Hey everybody, welcome back. Today we're going to be talking about a new approach to developing quantum algorithms known as linear combinations of unitaries. And the basic idea behind this is it gives you a way in order to do kind of something a little bit different than we had on using our previous paradigms. This gives us the ability to be able to add different unitaries rather than multiply them. And that gives us actually some really profound capabilities that we'll use in a number of applications in the upcoming lectures. So let me just share my screen and jump in to the stuff. So, okay, let me start with a particular example. So take the following quantum circuit. We begin with a 0. We then do a Hadamard transform, because we always do a Hadamard transform. Then we start with the state psi. And what we do is we will apply 2 gates, a 1 controlled U and a 0 controlled V. And then we perform a Hadamard transform. Now, if we were to measure this top qubit, then what the circuit will do is it will actually add together U and V conditioned upon the top qubit being 0. Now, let's actually just go through the analysis and validate this. So the analysis says, okay, we start with the state 0 psi. We apply the Hadamard transform. This maps it to 1 over root 2, 0 psi plus 1 psi. Now we apply the controlled U and the controlled V. The controlled V will apply a V gate to the 0 branch. And the controlled U will apply a U gate to the 1 branch. Now we apply the Hadamard transform again, and we get 1/2 0 U plus V psi plus 1 V minus U psi. The minus sign comes from the minus sign we get when we do a Hadamard transform on 1. So we can see that if we measure 1 on the first qubit, or actually let's say 0, then the state, if I define this state to be equal to phi, then phi gets mapped to the projector onto 0, tensor identity, divided, acting on phi, divided by the length of 0, 0, tensor identity phi, just by the axiom of measurement. Okay, so now we can apply this projector 0, 0, tensor I on the state, and we find conditioned upon this that we end up in the state 0 U plus V over 2 psi. Okay, and so furthermore, the probability of getting 0 specifically, that probability can be found by just computing the expectation value of the indicator function that counts all outcomes where this first qubit we're trying to measure is 0. And that boils down to 1/4 psi U dagger plus V dagger, U plus V acting on, oh, I said psi, I meant phi. Okay, oh, actually, no, sorry, I guess I did mean psi. Now, distributing it out, we have from multiplying the first terms and all the other cross terms that we end up getting, that this is equal to 1/2 1 plus psi u dagger v plus v dagger u psi over 2. And so that would be the probability of success. So this circuit actually ends up implementing non-deterministically the sum of two different unitaries. Now, this type of circuit, though, we've seen before. Recall that the Hadamard test ends up taking this particular form. In particular, the Hadamard test looks like Hadamard U Hadamard. So this can be viewed, if we measure the top, this can be viewed as mapping 0 psi down here. This can be viewed as mapping 0 psi goes to 0 identity plus u divided by 2 psi divided by the length of identity plus u over 2 acting on psi. Okay, so that is we can view the Hadamard test as being a way to end up implementing I plus u on a particular state for any u. And from the previous result, we noted that the probability of success was equal to 1/2 of 1 plus psi u dagger v plus v dagger u psi over 2. In the case where v is equal to the identity, then this is equal to 1/2 1 plus the real part of psi u psi. Okay, which agrees completely with the analysis that we did of the Hadamard test. So we can view the Hadamard test as a particular example of a linear combination of unitaries that ends up implementing 1 plus u. Similarly, we can end up viewing the swap test in the exact same light. So the swap test, it ended up looking like Hadamard. Here we have psi, and here we'd have some other state phi. Hadamard measure. And if you recall, the probability of measuring 0, we worked this out previously. And if you don't remember it, I recommend going through it. It's an easy exercise. The probability of measuring 0 is equal to 1/2 of 1 plus the absolute value of psi interproducted with phi squared. Okay, so that's how we used it before. But we can actually end up seeing this inside the context of linear combination of unitaries. What measuring 0 does is it will map the initial state of 0 psi phi maps to 0 identity plus the swap gate acting on psi phi divided by 2. Okay, now actually there's something kind of neat about this. Identity plus swap divided by 2, it turns out this is actually a projector. And it's a projector that projects onto the symmetric space, the symmetric subspace of span psi phi. And so the way that we can end up seeing that is, first off, swap squared is equal to identity. Well, why is that? Well, real easy, right? If we had a state, say 0, 1, and we swap it, well, then we'll get 1, 0. We swap again, we'll get 0, 1. Therefore, because swap squared is equal to identity. And by definition, This implies that swap is a reflection operator. Okay, so swap, since it's a reflection operator, has eigenvalues plus minus 1. Okay, cool. So let's take a look at what the swap operations, two eigenspaces are. So if we considered a state of the form, let's say we considered a state of the form phi psi plus psi phi divided by square root 2, we can very easily see that swap acting on this gives itself. Therefore, such states are +1 eigenvectors. Similarly, we end up getting that the states phi psi minus psi phi divided by root 2 are -1 eigenvectors. And furthermore, these characterize every possible eigenvector of the swap operation. So the swap operation has these two particular types, but what we're interested in, again, is we're interested in identity plus swap divided by 2. Okay, so if we consider identity plus swap over 2 acting on phi psi plus psi phi over root 2, we end up getting, just from the exact same eigenvalue discussion, we get that this is a +1 eigenstate, psi phi over root 2. However, if we do the exact same thing acting on phi psi minus psi phi divided by root 2, well, we will get phi psi minus psi phi divided by root 2 minus the swap gate acting on this. Well, its sign will end up getting flipped. Sorry, it'll be a plus. And then we'll get phi psi minus psi phi divided by root 2, which is equal to 0. So what we end up having is that now the two subspaces for this operator have eigenvalue 1 or 0. This implies that identity plus swap over 2 is a projection. And further, it's a projection onto the positive of the symmetric space, the subspace. And identity minus swap over 2 is a projection onto the anti-symmetric space. So really, what the swap test can be viewed as a way of doing is it uses linear combinations of unitaries in order to be able to implement a projector. And in general, if let R be a reflection operator, if we end up building Hadamard, controlled R, Hadamard, measure, then psi, if R, because R is reflection operator, every reflection operator can be written in the form identity minus twice a projector. We can end up seeing that basically what the linear combination of unitaries lemma ends up saying is that there's two outcomes. If we measure 0, then psi will map to identity plus r over 2, which is equal to 2 minus 2p over 2 psi. And if we get 1, then psi will map to identity minus r divided by 2, which is equal to p psi. So what this means is that all of these circuits that had this Hadamard controlled operation, Hadamard form, really what they're doing at a high level in all such cases is actually applying a projector onto a state. So one of the big uses of linear combinations of unitaries is to apply a projector. But this is just actually kind of like scratching the surface. Here, we've done an even weighted combination between two terms. It doesn't have to be even weight. So for example, what I could have done is I could have begun with 0, done a RY rotation in here, had a U gate, a V gate over here, RY dagger of some angle theta, and then measure. And by choosing the angle theta, we can end up changing the ratio between U and V that we end up getting. So let me just take you through this calculation. You probably won't use it in this form that much. You'll use it more in the next form that I end up giving, which is kind of the most general flavor of linear combinations of unitaries. But hopefully this will give you some intuition about how the next part of it ends up going. So we'll start with psi down here. Ry of theta acting on 0 is equal to cosine identity minus I, let's put a 2 in here because of that annoying factor of 2 in a definition. Cosine theta minus I sine theta y acting on 0, which will give us cosine theta 0 plus sine theta 1. Okay, and now when we apply the controlled U and the controlled V, tensoring all of this with psi, what we end up with is we end up with sine theta 1 U psi plus cosine theta 0 V psi. Okay, now we're going to do the RY rotation again. And now this will map to sine theta cos theta this will map to sine squared theta 0 U psi plus sine theta, I think that should be a minus, sine theta cos theta 1 U psi plus sine theta cos theta 1 V psi plus cosine squared theta U psi 0. Okay, cool. And so if we take a look at this and add everything all up, what we end up getting is, if we measure 0. Then using trig identities, this will end up going to cosine cosine of 2 theta u plus v over 2. No, actually, sorry, that's really wrong. This will just, let's collect the two terms. This will end up going to cosine squared theta u minus, or minus sine squared theta v psi. Okay, and then, yeah, the other one will end up giving us sine theta cos theta 1 u plus v over 2 psi. All right, and so then this is our final expression that we end up getting, and we can reweight in the 0 branch over here the combination between u and v that we end up getting in it. So that's the general idea that we can do. And so taking that particular form, let's actually kind of generalize it even further. Ideally, we'd like to do more than just summing two different unitaries together. We'd like to have a way of building an arbitrary sum of different unitary terms. And so in particular, what we'd like to be able to build is we'd like to be able to build something that looks like sum over aj uj. Now, without loss of generality, we're going to assume that a sub j is greater than or equal to 0. Why can we do this? Well, we can do this because of the fact that imagine that a sub j were less than 0. Then what we can do is we can say, okay, well, a sub j uj is equal to negative aj negative uj, which of course is equal to the absolute value of aj negative uj. So we can just take the sign from the AJs and absorb it in the definition of the unitary. Now, if we assume that we ended up having a complex phase, like let's let a sub j equal absolute value of a sub j e to the I theta, then what we can do is we can say, all right, well, a sub j, u sub j then can be written as absolute value of a sub j times e to the I theta u sub j, where again, each of these u sub j's is a particular unitary matrix. All right, so we can take signs, or more broadly, any phase that we have associated with a particular coefficient and just absorb it into the unitary. This is, technically speaking, not really fully necessary. It makes some of the algebra that we're going to be doing in the next couple of steps a lot more self-explanatory. Okay, so we're just going to assume that all of these guys are positive, and if there's any phases or signs, all of those are just absorbed into the definition of the u sub j's. All right, so we'd like to be able to build this, and the way we're going to build this is we're going to have two ways of providing to our quantum algorithm the values of the a sub j and the u sub j's. And we're going to use two subroutines for doing this. The subroutine that we will use for making the a sub j's is a subroutine we're going to call prepare. Now, prepare has the property that prepare, acting on 0, will map us to a sum over j of a sub j square root divided by the square root of the sum of a sub j. J. Now this over here, just because I don't want to have to always talk about the normalization, we're going to write this in the following way. We're going to write this as divided by the square root of A. Okay. And so now what we end up getting from this is we end up getting a way that we can load in the coefficients of the linear combination of unitaries using this prepare operation. The next operation that we need has to load in the u sub j's. And what this one ends up doing is it will take j and some quantum state psi and map that to j u sub j psi. Okay, so these are the two basic operations. And actually, believe it or not, it's all we need in order to be able to understand how to build the sum of unitaries. The way that we're going to do this is we're going to do the following. Our algorithm will begin with a whole bunch of ancillary qubits that we're going to prepare in the zero state. Then we've got some quantum state psi to begin with. We start by gluing in the A sub j's into the amplitudes in the top register. Then we apply select, and then we're going to apply the adjoint of prepare. And if all zeros are measured here, then we get psi goes to sum over j, a sub j, u sub j, divided by a psi. Okay, let's go through a proof of this first. So to begin with, we end up having 0. Now we apply prepare to that. Oh, and tensor psi. That will map us to the sum over j, a sub j, j psi, divided by square root a sub a, and there should be a square root here. Now we apply select, and what select will do is that will map this to a sub j divided by square root a j u sub j psi. Now we apply prepare dagger, and this part is really lame, so I apologize wholeheartedly for this, but the actual expression that we finally get in the end for this is going to be prepare dagger sum over j square root a sub j over square root a j u sub j psi. Okay, I know, right? We were probably hoping for something grander, but what we wanted to do is we wanted to be able to say that we have this circuit. Recall that we've got prepare dagger, and then we feed that. We've had the select, and we had the prepare over here. And we want all of these to be 0. So for the moment, let's just imagine that we were to measure all of those qubits and hope that we end up getting 0. Okay? In the event that we get 0, then the state, which I'll call chi, will map to only the component of the state chi that's consistent with those measurement outcomes up here, 0, which can be written algebraically as the projection onto 0, tensor identity acting on the psi state, acting on this register chi. Now, actually, because prepare acting on 0 is equal to sum over j square root a sub j over square root a j, we end up having, under the assumption that all the components are real, that prepare dagger left acting on it is just the adjoint of all of this stuff over here. And so therefore this is equal to sum over j square root a sub j over square root a j. Again, ordinarily there would be complex conjugates for this, but because we've assumed all the A sub j's are positive and real, we don't need to worry about the complex conjugates. Okay, actually, let me change the variable summation to k. So now, if I substitute that in, then this projection onto 0 ends up becoming sum over k square root a sub k, over square root a, k, sum over j, square root a sub j over a, u sub j, psi. Now, this inner product between that vector and that vector is zero unless k is equal to j. So therefore, we can compress this to just sum over j, a sub j over a, u sub j psi, which is exactly the linear combination of unitaries that we were looking for. So we can see that another way of putting it is that the resultant state that flies out the end, right, will have a whole bunch of different components, but we can envision that the final state over here will have a projection on 0 that will end up giving us the state that we're interested in, which is the linear combination sum over j, a sub j, uj psi. Now, another way of visualizing this is through this language known as a block encoding. So the reason why we come up with a block encoding is that let's let A be equal to the sum over j, a sub j over a, u sub j. Then the transformation that we're trying to do is psi goes to a psi. All right, wonderful. So the way that we're doing this is we're actually, if you think about it, embedding A inside a larger matrix. So the way that we're doing this is we're using this prep select prep to build a larger matrix such that when the input is 0 over here and the output is 0 there, then psi maps to a psi over the normalization constant. So that is, we can view this in the language of block matrices in the following way. Okay, where here, what we have is we've got the input. The inputs over here, 0 and 1. And the outputs are the column associated with it. Or sorry, I guess the outputs are the row and the inputs are the column. So we're interested in the case where our input is 0 and our output is 0. And we've seen here from the previous analysis that the matrix over here that we end up implementing is A over alpha, A over little a in this case, where little a serves as a normalization constant. And why is little a needed if we're trying to implement capital A? Well, the reason why is that A can be really any matrix. And so A, the norm of A, could be equal to 10 to the 24, say. But the norm of the entire matrix, let's say Q out here, has to satisfy Q equals 1. So if we're trying to embed a arbitrary matrix inside a larger unitary matrix, something's got to give, because there's no way that we could end up having an enormous normed matrix as a submatrix of a unitary matrix, because the norms of every row and column of a unitary matrix have to be 1. And so another way of understanding this is that normalization constant is exactly what's needed in order to make sure that we can actually do this without violating the unitarity assumptions of the larger matrix. So this is a block encoding. And in general, we've got some language that we use for this. Let's say that what we want to implement is A, and what we actually implement is A tilde. Then we say that this unitary Q is a M epsilon block encoding of A if 1, the normalization constant equals A, which it is here. 2, if M qubits are needed for the prep circuit. And 3, if the norm between A minus A tilde is less than or equal to epsilon. Okay, so that is the definition of a block encoding. First one is a normalization. Second one is a amount of extra memory that we need in order to be able to build the block. And the third is any error that ends up creeping in because of our use of a block encoding. Now, this shows us how we can end up building any particular matrix, but it's not necessarily clear, right? What family of matrices could we actually end up implementing with this? Well, actually, it's pretty broad. So all square matrices can be written as a sum of unitaries. And the reason why is actually, you can see it quite easily from the properties of Pauli operators. Pauli operators are unitary. And further, they form a orthonormal operator basis, where the notion of the inner product on this space of matrices for the Pauli operators ends up going, the inner product between, say, a matrix A and B is equal to 1 over the dimension of the space times the trace of the product between the two. And actually, it's very easy, as we saw earlier, using the anti-symmetry property of Pauli operators and the symmetry property of the trace, to note that for any two Pauli operators, trace of P and Q is equal to 1 over D delta PQ. Okay, so it's 1 if the two are equal and 0 if it's not, like we would normally expect for an orthonormal basis. Now, if we've got a matrix A, then the coefficient in the expansion A sub j is actually just equal to the inner product of the jth Pauli operator in our basis and the matrix A. And then once we end up making this assignment, then we can end up writing A as the sum over J, A sub J, Pj. So in general, we can, using the techniques that we've already discussed and developed, using poly operators as an orthonormal basis, we can always end up writing our operator as a sum of poly operators. Since the poly operators are unitary, this is a sum of unitaries. So any non-unitary matrix can be written in this particular way. And so this is one of the reasons why linear combination of unitaries is so kind of powerful, because it allows us to be able to implement, at least non-deterministically, any linear algebraic operation that we find interesting. So there's a number of different opportunities that this ends up raising, and we'll go into some of them in greater detail. But let me just kind of whet your appetite by showing you one particular case. Let's consider that what we want to implement is we want to implement e to the negative I u t, where u is a particular unitary. Well, this over here, and let's assume here that u is equal to u dagger. All right, well, this we can write as sum from j equals 0 to infinity negative I t to the j over j factorial u to the j. So if we define our prepare operation to map this to 0, maps 0 to the sum over j t to the j over j factorial square root. Now we've got a normalization factor in here that we need to worry about. Yeah, it turns out to be e to the t. If we sum that to infinity, j, then select, we can end up picking, so that select is, we'll take j psi and map that to j negative I to the j u to the j psi. Now recall that we chose the convention that all the coefficients in the expansion will be positive. So because of that, we have to absorb the negative i's inside the definition of the unitaries. And so that's why select ends up taking this particular form. So then if we had an unbounded number of ancillary qubits, we could then simply do the following. Okay, and then once we've done that, post-selected upon success, we will end up producing the operation psi maps to e to the negative I u t psi. However, one of the problems is that the probability of success, if t is large, actually isn't going to be all that good. The reason why is that this operation q will end up block encoding an operation that ends up going like e to the negative I u t over e to the t. Okay, and we can end up seeing that the probability of applying this operation to psi properly, the probability of that goes like 1 over e to the t. Okay, so that is pretty lousy. So we would like to be able to come up with a good way to be able to boost that. If we wanted to do this operation just once, well, we could use amplitude amplification. But the problem is that that's going to turn out to not be terribly convenient because we still have to boost this exponentially small probability up to something that would be large if we wanted to look at this in a case where t is large. So next time, we're going to be discussing a new flavor of amplitude amplification that we can use in order to boost the probability of success from this minuscule amount that we have here to something that's actually serviceable. And that technique is called Oblivious amplitude amplification, and it's a cornerstone behind making what otherwise would be this cute trick that you can use to sum unitaries together to be one of the most powerful computational paradigms that we've discovered in quantum computing. Well, thank you very much, and see you all next time.